This is Boomer. She's super cute. She's here to help you learn about physics. She's going to show you about this problem because this problem involves a cat and she really loves cats. Right, Boom Boom? Okay, so she's going to stand by. She's only about 60 pounds. Okay, this is the continuation of our problem set number 8. We have just found that this eye of a rod pivoted at the center is 1/12 L squared. Here we go. And we're going to now add it to a hoop, which is R squared. But this hoop happens to have a very nice R value that's actually L over 2. The whole thing squared, that's L squared over 4. So our I total for this assembly is going to be 1/12 L squared plus 1/4 L squared. So 1/4 can be written as 3/12. This is going to give us 4/12 L squared. But we know that we can rewrite 4/12 L squared as 1/3 L squared. So that's now our I value for our system. That's part B. Then it seems that this lovely cat is going to grab onto a string that's around it. The cat conveniently is also mass M, just like the rod and the hoop. So here's our cat. Here we go. Okay, so it's asking us to find tension, acceleration of our cat, and the angular acceleration of our whole system. So we can do several things. Let's rate forces for our cat first. So on our cat, you should see there's tension pulling up, and there is mg pulling down. So for our cat, we will sum the forces. We will set them equal to ma. We will have mg winning. We will have tension losing equals ma. So we can solve for tension or whatever. We can't solve for A, so we have two unknowns. So let's stop. Let's move over to our disk. So on our disk, we have tension pulling down on our disk like this. That's the only force that is going to cause rotation. The disk and the hoop assembly do have some mg down right here, but it's balanced by a normal force up from the pivot. And those don't create any torque anyway because they have no lever arm. So let's go in and let's sum the torques and set them equal to I alpha. Our torque is only tension. Remember, torque is a force times a distance. It's at distance r. Oh wait, but r again is this lovely L over 2. So that's force times a distance, that's our torque. Our I value we found above, 1/3 L squared. And we can rewrite alpha as, if we'd like to, as A over R. Where again, R is L over 2. So this is going to simplify nicely because we have an L on the bottom here. We can bring that 2 up to the top. And then we have another L here, so those will end up canceling. So we're going to have T equals, all our L's cancel. We're going to have 2/3. Ooh, we still have a half here. 2/3 M. Let's multiply by 2 then. Okay, so our tension is 4/3 of our MA value. Okay. That will allow us to plug in up here. So let's go ahead and combine these two. So when I combine these two, I come out with having mg minus, instead of writing T, let's just write all this, 4/3 MA. It's going to equal MA. These are all the same M. So let's add this to the other side. So we're going to add it to the other side. So it's going to look like this. Now we have 4/3 MA plus more MA. So 4/3 plus 1. That's 4/3 plus 3/3. So that's 7/3 MA. Our M's cancel. We discovered that our acceleration is 3/7 of gravity. And there's several ways to check our answer here. One, we didn't get an acceleration larger than the value of gravity. Good. Also, we didn't get the value of gravity. Good. Also, our units work out. Acceleration and gravity have the same units. So it's all seeming pretty good here. We do have to do a little bit more work to actually fully answer the question, although it's not a big deal. We just have to say, oh, listen, we now know A, so we can actually tell you what tension is. 4/3 m times 3/7 g. So that's just going to simplify to 4/7 mg. So tension. So those are our results so far. And also asks us for alpha, but we know alpha equals A over R, so we can just take our A value, 3/7 g, and we can divide by our R, which is L over 2. This 2 actually flips up, so we're going to get 5/7 g over L. The last question is about momentum, and the angular momentum of the cat around the edge, which could seem really hard because you might think that the R value is perpetually changing, right? Here, and then the cat goes further, and so it's here. But remember that angular momentum is just R cross P, where our R value is always going to be L over 2. And so now all we have to do is find our momentum, which is mass times velocity. And so we can just find velocity based on the height of descent here. They're going to descend down 5L over 3. So our goal is to find this V to plug in here. Or we can say, oh, look at this. I know my acceleration. I know my distance. I want to find my final velocity. So I can say V final equals squared V initial plus 2 times my acceleration 2a delta x, where they tell us h is the distance we're interested in. It's 5L over 3. So our final velocity is 3's cancel, square root of 10/7, right? 2 times 5 is 10, 3's cancel off of the 7, GL. So that's what's going to go here. So our angular momentum, the R cross part, ended up being easy, just the radius, then the mass, then the velocity at this location that they're asking us about, which we just did kinematics for. Square root 10/7 G. So remember the R cross. That's a convenient thing to do. Okay, there you go.